When we want to divide rational expressions, we engage two familiar skill sets. The skill set that we just developed for multiplying rational expressions and the skill set that we developed 5 to 7 years ago on how to divide fractions. If you recall, for dividing a fraction, we never really want to divide by a fraction. We want to multiply by its reciprocal. And we're going to do the same thing here for the rational expressions. Now, with these rational expressions, we have the extra consideration of those restricted values of x that don't fall into the domain of this particular expression, what we're allowed to use as inputs. So if we go through the factorization right from the beginning, we should see that our numerator of the first fraction will factor as x plus 5 and x minus 2. Our denominator is just a monomial, so we'll keep it the same. At this point, we're still in division, and we're going to factor again the numerator of the second fraction and the denominator of the second fraction. Looking at these two denominators, we see that we're going to have restricted values of x of 0 and 3. Both of those numbers have the possibility of making the denominators equal to 0. 0 would work in both the first fraction and the second one. 3, of course, working in that second factor of the second fraction. Once we flip over the second fraction into its reciprocal in order to complete the division, we will have to give a consideration again to potential restricted values because of the role that that numerator is then going to play as a divisor. So we're going to leave our first fraction the same. We're going to change our operation to multiplication, and we want the reciprocal of the second fraction. We see that we still have the factor of x minus 3, which is going to contribute a restricted value of 3. We still have this factor, which contributes the restricted value of 0. But from here, we have another restricted value that we're not able to use for x, which is x is equal to 2. So we are allowed to do the simplifying that we're about to engage in, provided that x is not any of those three numbers. We're going to cross out x minus 2s. We're going to cross out the x minus 3s. We're going to cross out these x's as all divisions that get done as simplifications, leaving us with a final simplified version of x plus 5 over 2. In our next example, we're going to engage in a similar set of operations, but first understanding that just because we don't have a denominator of this first binomial doesn't mean that there isn't actually a denominator there. We see our first numerator is a difference of squares. And we're going to leave the 1 for the sake of being exact. Still division, nothing to factor over here. At this point, we have no restricted values. Our two denominators are 1 and 9. They will never be 0 because they are both 1 and 9. We don't have to worry about them being 0, but when we use the reciprocal of the second fraction, we see that we move the expression 7 minus 3x to the denominator. That expression, equaling 0, gives us a restricted value of 7 over 3. We don't see any exact matches in order to do our divisions. However, we do have that this denominator and this factor of the numerator from the first fraction are opposites of each other. So when they divide, they leave behind a negative 1, leaving us with a 3x plus 7 from the first factor, a 9 from the second, and the negative from the division. If we want to clean that up at all, we can say negative 9 times 3x plus 7.